Good morning, I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next lecture that is related to equalization. So, equalization is basically when we are transferring the information over the channel, it will be affected with noise, then pulse shaping will be done at the receiver side, which is a part of equalization technique. So, there are different types of filters are there that will be doing work of equalization, like the transversal filter, adaptive filter, zero forcing equalizer, decision, feedback equalizer. So, these we are going to discuss in today's lecture. So, first we will see what is channel estimation techniques, how we are going to estimate that whether equalization is required or not. So, channel estimation is an autoregressive process that may be performed with a number of iterations, which means whenever the input signal will change, the iterations will be there. Number of iterations means number of repetitions the particular algorithm will going to work, so that the channel will be estimated. We have to estimate the value at the receiver side. Let's say I have transmitted this particular alphabet, that alphabet means particular signal will be transmitted, which is denoted by this A1. Then it will going to travel over the channel. At the receiver side, we are going to receive A1 cap. Now, what is A1 cap? A1 cap is nothing, it is the estimation of the original signal A1, because it will definitely going to, in practical conditions, it will going to it will be affected with noise only. So, that will be noted by this A1 cap, that is the estimation value of the original signal A1. So, an autoregressive model specifies that the output variable depends linearly on its own previous values or some known values. So, iterations mean repetitions. So, it will depend on the previous values and some of the parameters that are already known to you. Now, channel estimation is the estimation of the channel impulse response, that is CIR, at the receiver side. So, three different techniques of channel estimation are there, like first one is the CSI based, that is using this pilot or training sequence based. Second one is the blind, that is statistical data or prior knowledge based. Third one is the semi blind. So, basically three different types of channel estimation techniques are possible. Now, the channel impulse response estimation basic is channel process are wide sense stationary, that is WSS. It is a stationary process, but it is wide sense. Then conceptually, on a stationary wireless channel, if an impulse is transmitted, then multiple delayed version of impulses will be received at the receiver side at different instants of time. So, which means whenever the signal will travel over multiple paths, then we are going to receive the delayed version of the transmitted signal. So, these impulses are non-correlated to each other, and with reducing amplitudes with time, they are just like delayed samples, and hence a differential equation with coefficient values can be correlated with this concept. So, FIR filter model is adopted over here, that is a finite impulse response, because when we are talking about IIR filter, it is an infinite impulse response, it is of no use. So, basically we are using the FIR filter for the purpose of channel estimation. So, the impulse response is a time varying and can be represented by this equation, that is Yn is equals to HEN convolution with Xn. Xn is nothing, it is the input signal, plus Wn. Now, Wn is nothing, it is the noise which will going to affect the particular channel. Now, next state estimation is based on Hn plus 1, which is equals to AHN plus Wn. Now, Wn is nothing, it is again noise. So, this is the shifted version of the channel impulse response. Now, A is the coefficient value to estimate the next channel state. Now, this is the comparison of the different channel estimation techniques, like first one is the training sequence based, and next is the blind method. Now, the training sequence based method, the sequences known to the receiver are embedded into the frame and sent over the channel. In this case, no training sequence is required, but the method uses certain underlying mathematical properties of the data being that are being sent together. So, that is the blind method. Now, it is easy and very popular. It consumes high bandwidth So this training sequence consumes a higher bandwidth. It is computationally, it is not too intensive, but here it is extremely intensive. That is the blind method. Now the major drawback is that it is a waste of information bandwidth, and in this case it is bandwidth efficient. So that is the difference between comparison of the training sequence and blind based method. Now next is the equalization technique. So the term equalization can be used to describe any circuit or signal processing operation that minimizes the ISI, that is inter-symbol interference. So whatever circuit that will going to minimize the ISI, which is being responsible when single channel is used for the purpose of transmission. We are not using any diversity technique. Diversity is also used to reduce the ISI. So equalization is a technique where we are also we will going to design a circuit that will going to minimize the ISI. Now the purpose of an equalizer is to reduce the ISI as much as possible to minimize the probability of wrong decisions. So let's say this is an signal that is denoted by SN. It will be passed through a filter, you can say a distortion that has a transfer function given by HF. Now it will going to travel over this channel. This channel is having a noise that is denoted by WN, and then it will be passed through an equalizer whose transfer function is inverse of that distortion. So whatever distortion has taken place over the transmitter, at the transmitter side or over the channel, if we are going to take the inverse transfer function of that particular distortion, then it will be received over here. This is SN. This is S dash, and this is again the estimated of the transmitted signal. Now this is Rn, that is the signal which is received. It is equals to Hn star Sn plus Wn. Now Wn is nothing, it is the noise. So an equalizer is an inverse channel filter to mitigate the unpredicted channel problems. Now the channel equalization concept in a digital communication system using matched filter and decision making. So how we are going to estimate using this matched filter? So this is a very simple diagram. Here the SN signal which we want to transmit at the transmitter side, it will going to travel over the channel. Now at the receiver we have to use a matched filter. Now to this matched filter, it will be passed through this particular filter which will be having their own characteristics. Then a threshold value will be set over here, and then the decision has to be taken that since it is a discrete system, then we have to consider whether 1 has been received or 0 has been received. So this is nothing, it is the estimation of the original signal that you have transmitted. Now next is the transversal filter, that is an example of equalization filter, a type of equalization filter. Now transversal filter is essentially a tapped delay line with feed forward taps, means there is no feedback is used, it is a feed forward tap forming a finite impulse response filter. Now each delay element delays the input signal as it propagates through the filter. So basically there are different delay elements are there. In Z transform we can say that if Xn is passed through a filter whose delay is Z inverse, then Xn minus 1 will be there. If it is Z to the power minus 2, then it will be Xn minus 2, or you can use 2 Z inverse blocks in cascade, 3 Z inverse blocks in cascade. So this means it is a 1 unit delay. So that's what it is written over here. Delay elements will also be used. Now the delayed version of the signal, that is Yt minus Kt, where K is will vary from 1, 2, 3 up to so on, are the tap coefficients, and T is the period by which the signal is delayed. Now the integrated filters transfer function can be adaptively adjusted by changing the coefficients, that is C0 up to Ck of its tap weights. Now adjusting the tap weights, let us adapt zeros in the overall transfer characteristics of the filter to various frequencies, and that will going to implement the different filter characteristics. So it is basically a linear method of equalization. Now next, this diagram is showing the transversal filter, and this is showing the multiplierless. There is no multiplier multiplierless transversal filter is there. So in case of this transversal filter, you can see that there are 1 unit delay elements are used. So whatever input is given, like yn is there, then yn minus 1 there, then at the output of the second delay element yn minus 2 will be there, and at the output of this n minus 1 delay element there will be yn into yn minus n minus 1 output will be there. Now these are passed through different weight functions, these are sum up together and we are going to estimate the value. So this is a very simple transversal filter, that is an example of equalization filter. Now next one is multiplierless, where though no multipliers are used, it is the yn signal is passed through linear to logarithmic, where it will going to convert the multiplication by addition. So additions are there. Now you can see that here multiplication is used and it is changed to addition. So that's why we have used a logarithmic scale where we are not using any multiplier. So linear to log is there, it is passed through this delay element, and then at the output it is again converted from log to linear value and then sum up together, and then we are getting the y dash n value. So initially we are using converting linear to log, and at the end also we are converting linear to log value. Now next one is the zero forcing equalizer, that is also an example of equalizer technique. In this case, it refers to a form of linear equalization algorithm that is used in communication system which applies the inverse of the frequency response of the channel. The name of zero forcing corresponds to bringing down the intersymbol interference to 0 in a noise free case. So zero forcing equalizer basically used to reduce the ISI, although all the equalizers are used to reduce the ISI, but here it has to be reduced to 0. So this will be useful when ISI is significant as compared to the noise. So there are ISI and noise, both are different things. When ISI is much greater as compared to the noise, then zero forcing equalizers are used. So for a channel with frequency response f, the zero forcing equalizer CF is constructed which is the inverse of this frequency response, channel frequency response. So thus the combination of this channel in equalizer gives a flat frequency response with a linear phase that is given by FF into CF, which is equals to 1. So this is an example of zero forcing equalizer. Next one is the adaptive equalizer. It is a non-linear equalizer that automatically adapts to time varying properties of the communication channel. Adaptive equalizer can control the tap weight. So you can see that the tap weight over here will be controllable by this feedback which will be generated from this matched filter. So it can control the tap weights on the basis of estimated channel coefficients from the received training sequences. So this is the input signal we want to transmit, we want to estimate its value. It will travel over a channel, then tap weights will be there, that will be operated by this training sequence. Now this training sequence is fixed in nature, it will going to change the tap weights depending on which particular section we are getting highest signal to noise ratio. Then it is passed through this matched filter, then decision has to be made, and these are the decision making device, and then we can estimate the signal, that is denoted by S-n. Next one is the decision feedback equalizer, that is a fourth kind of equalizer. So it augments a linear equalizer by adding filtered version of the previous symbol estimate to the original filtered data. Now you can see over here that this is passed through a channel, there will be a feedback that has been set up. Feedback and feed forward both are used. So it will going to adjust the tap weights depending on the feedback filter. And here again match filter and a decision device will be there, which will be delay of delta is being generated through this particular system. So a decision feedback equalizer is there, where feedback and feed forward both techniques are used. Now the last one is the least square and LMS algorithm, that is the most important equalizer that is available. So, in this case LS means least square, means that the overall solution minimizes the sum of the square of error made in the result of every single equation. So, in every single equation whatever we are going to write, it means that the overall solution will going to minimize the sum of square of the error. So, the LS and LMS algorithm represent the regression process to adapt the system continuously. LMS algorithm are a class of adaptive filters which is used to mimic a desired filter by finding the filter coefficients that relate to producing the LMS of the error signal. Now, it is basically a stochastic gradient descent method in which the filter is adapted because on the error at the current time. So, you can see in this diagram also that this is the input signal that is denoted by xn. It will apply to this unknown system channel which is having this transfer function denoted by this hn. It will be the output of this will be yn. It will be affected by this noise and then an adaptive filter output will be generated. So, this is an LMS technique. So, in this lecture we have discussed about equalization, where it will be used to minimize the ISI, that is inter-symbol interference, and then 4 to 5 different types of equalizers we have discussed in this lecture. Thank you.